So in that video, that was just a classic example of a phenomenon in physics called the Doppler effect, which pertains to waves and perceived frequencies based on speed and position. The Doppler effect is defined as the increase or decrease in the frequency of sound, light, or another wave as the source and observer move toward each other. The effect causes a sudden change in pitch that can be noticed when the truck in the video is approaching the camera and when it's moving away. When the source of the wave is approaching, the preserved frequency of the sound of the car horn is noticeably higher than the actual frequency that is produced by the source, which is the car horn. The frequency of the waves pertains to the number of waves that pass at a point in a given time. So these diagrams are just a simple representation of the Doppler effect pertaining to sound waves. In each diagram, you can see a black dot, which represents the source of the sound waves. And then the arrows, the orange ones, represent the vector of velocity of the moving object. And then obviously you got our stickman observers. And then these circles represent waves, and the blue highlighted waves represent the perceived frequency of those waves. In the approaching diagram, we can see that the observer here is being subjected to a high density of waves, which is correlated to the high frequency that people experience when a source is moving towards them. That's why in the video, when the truck was approaching us, the car horn sounded a lot higher pitched than here. When the truck was pretty much parallel, that is the best representation of the actual frequency that we should hear if, per se, that the car was standing still and we were standing right in front of the truck and the horn. And then as the truck moves away, that's when we see kind of like a lag in the sound waves themselves. And that's why the highlighted are kind of like spread it out, because there's a lower frequency of sound waves that are being observed. So for quantitative purposes, these equations are used to find the perceived frequency when a source is approaching and as well as when it's receding. In this equation, F plus represents the perceived frequency when the source is approaching you. Fs represents the actual frequency of the source that the sound waves are coming from. And then Fs is also the velocity of the source, which the sound waves are coming from. And then V represents the speed of waves, which is typically represented of the constant 343 meters per second. Similarly, in the receding source equation, F minus just represents the frequency of the receding source. Fs, or F source, represents the same thing as Fs. The only difference between this equation and instead of subtracting one from Fs over Vs over V, you're adding to 1. So another interesting thing about the Doppler effect is that it's associated with shock waves. And shock waves are when the source of a wave is moving at such a speed that it exceeds the speed of the waves themselves. And this is commonly observed in supersonic flight when a fighter jet, per se, creates a sonic boom. And the thunder sound that comes from the sonic boom is produced by the jet, actually travels behind the jet itself. And if you've ever been to an air show, you notice that as a jet passes over you, if it is going supersonic, that you don't hear it exactly when it passes over you, and more or less it sounds delayed. And in this diagram, it kind of represents that. As the jet is moving forward, the sound waves are actually traveling behind it, and that's when you would observe the sonic boom itself. One interesting thing, though, outside of shock waves pertaining to sonic boom and sound, is that wave speed actually can be influenced by the media or environment that the waves are in themselves. And this can be seen in boats. When they're traveling through the water, they produce waves that are behind the boat itself. And that's because the boat is traveling faster than the waves can themselves, because the media is slowing down the waves that are being produced. On a similar note, sound waves aren't the only type of wave that experience the Doppler effect. Light waves also can experience this phenomenon and is most commonly observed in space. If a source of light waves is receding from you, the wavelength of the light that you perceive is longer than the actual source of wavelength of light themselves. This is called the redshift and is commonly found in faraway stellar bodies in space. And stellar bodies typically consist of suns, galaxies, and a whole plethora of different astronomical bodies. And in this diagram, you can see this is representing a stellar body or a sun. And then this is an observer or just another planet. And as the sun, as well as other stellar bodies, move away from us because the universe is ever expanding, as it moves away, the wavelength of light actually starts to dissipate and lengthen, which causes this red shift. And lengthened wavelengths is associated on the electromagnetic spectrum with the color red. So what we have here is a pretty realistic representation of a problem that you might come across pertaining to the Doppler effect. So in this question, a car is passing you going 45 miles per hour while honking on their horn at you. If the frequency of the car is 30 hertz, what is perceived frequency of the horn as the car approaches you and as it is receding from you? So to begin this problem, what you typically want to do is list out the variables that you're given. In this question, V which would represent the velocity of the waves that we're trying to find, which is sound, and that is usually at a constant of 343 meters per second. Fs is the frequency source, which is given by the frequency of the car horn, which is 300 hertz. Vs is velocity of the source, which is given as well at 45 miles per hour. The only problem with this is that this is not in standard units, so in order to get it to standard units, which is meters per second, what we would have to do is convert miles to meters, which can be seen here, multiplying 45 by 1,609 miles, which gets us to 72,420 meters. And since there's 3,600 seconds in an hour, we just divide that 72,420 meters by 3,600 seconds to get our velocity of the source, which is 20 meters per second. From this, we can use the approaching formula for the Doppler effect in order to solve the first part of our equation. So in this equation, as previously stated, F positive is the frequency of an approaching source, which is equal to frequency of the source given divided by 1 minus velocity of the source divided by velocity of the waves. And then all we do is plug in the variables that we're given, which will get us to 319 hertz. And according to the Doppler effect, this should be correct, as since the source is approaching us, the frequency should increase, which in this case it does. For the receding frequency, it's a similar equation. The only difference is instead of subtracting 1 from the division of velocity of the source and the velocity of the waves, you're adding 1 in order to decrease in the denominator the overall frequency or velocity. So if we plug in our variables, we should get a lower number, which we do at 203 hertz. So in conclusion, the Doppler effect pertains to waves and the change of perception and frequency based on the movement of the source of the waves to the observer. And it is commonly found in the world involving sound waves being observed with sirens and cars passing people. It is also observed in astronomy pertaining to the redshift when light produced by a stellar body has changed in perceived wavelength because of the source moving away from the observer. The Doppler effect is also correlated with the phenomena of shock waves and sonic booms when the source of a wave is moving faster than the waves themselves, such as when sonic jets are moving at supersonic speed. Thank you again for watching the video, and I hope you learned something and enjoyed.